So let's take a look at gases. What's so special about gases? Well, first thing you'll notice is the format of these slides bears no resemblance to any of the others. This was a set of slides I inherited from my predecessor, who's now deceased. But I thought they were better than the ones I got from the publisher, so I stayed with these. Gases, we know how to characterize gases, of course, but in a historical sense, gases led the way to everything else in modern chemistry. And for practical reasons, because when modern science was starting to get rolling in the late 17th century, scientists knew how to work with gases. They knew how to measure volumes. They knew how to, eventually they knew how to measure pressures. And we'll talk about that in a minute. But at least from a physical standpoint, you got one gas, you can measure things about that gas, and it works for any gas. They all seem to behave the same way, physically speaking. And that facilitated chemical investigations. So what are these unique qualities of gases? They behave as independent particles. We say semi-independent because they do interact some, but on a microscopic scale, the particles are so far apart that on a statistical basis, their impacts with one another and their encounters are relatively infrequent as compared to solids and liquids. So they behave as independent particles. And in fact, an ideal gas is treated as if all the particles were independent. Well, actually, an ideal gas is treated as if the particles don't exist. But that's another topic, and we'll get to it in a minute. So we treat gases as rapidly moving atoms or molecules, and there's ample evidence to suggest that they are rapidly moving. In fact, we can measure their velocities. And we'll get to that at the end of the chapter. Measure, more like calculate. All gases are miscible in one another. In other words, when you put two gases together, you always get a homogeneous mixture, a solution. So the air we breathe now is primarily a solution of nitrogen gas and oxygen gas, with a little less than 1% argon and then some minor components. But they're all miscible in one another because there's plenty of room. I mean, there's so much room between particles, you can slip anything in there as long as it's a gas. They do have mass, which means if they're moving fast and they have mass, they have kinetic energy. That's from physics. If you know the velocity of an object, you know its mass, you can calculate its kinetic energy. In other words, if it slams into something and stops, then all that energy is transferred to the other object, or in terms of motion, or it's converted into heat. Right? You can't, that's one of the basic principles of physics. Energy can't be created or destroyed. So if it's got a lot of energy and suddenly it stops, that energy's got to go somewhere. We have to treat them as if all these individual particles, we have to treat them as if they're in random motion, because there are just too many of them to track every particle. Even though the distance between them is relatively far apart, as compared to their size is really small, and then the distance is far apart. We don't have the computing power to follow every atom or every molecule in a gas. So we treat them statistically. We treat them as if they're moving randomly. Now, if theoretically, if we could track every particle and all the impacts and measure them all, we could determine the outcome. But we're not there yet. So we're going to look at first actually in historical sequence, we're going to look at the gas laws. In other words, those descriptions of gas behavior that were accumulated over time and led to theories about how gases actually operate. So we're going to look at the laws first. And of course, we're going to treat all these gases as if they're ideal. And I'll give you a definition of that in a few minutes. We're going to learn how to use these gas laws to solve problems, including the ideal gas equation. And I partition gas laws into two different types. I'll just give you a preview. They're I call them the before after and the state. So with the gas laws, most of them, the gas laws, if you know the before conditions and some of the after conditions, you can solve for the missing one. However, if you only know how the gas exists right now, you don't know how it got there, then you need to approach it from a state equation, which is the ideal gas law. So I'll give that to you in a minute. All right. We study gases not just for their historical significance and how they lead us to understand chemical reactions, but as a practical matter, since the Earth is covered in gas, right? We need to know, how it behaves, and that's the Earth's atmosphere. Right? We know it's necessary for life. We know it becomes polluted often, not so much in this country anymore, but in places like China, their situation is worse than ours ever was. And the only reason you go visit China during, say, the Olympic Games and you have clean air is because they shut the whole place down, so the air will clean up. But under normal circumstances, it's one entire nation of smog, which is a portmanteau for smoke and fog. Now, here's where I deviate from the authors. Pollution and global warming have a tenuous attachment to one another's at best. The man-caused global warming. Now, there's no denying that the Earth does get warmer and it does get colder over time. And we see that both in our historical record and in the geologic record. We see evidence of periods in the Earth's history where it was extremely hot or extremely cold. But the attempts of the, I guess I could call them religionists, they're not really scientists, who attempt to blame current global conditions on human activity are way off base. They really don't have a scientific leg to stand on. The reason they come out with these reports in support of man-caused global warming is because that's where the money is. When the governments are funding this research, and you're going to tell them what they want to hear. Unfortunately, science is a human endeavor, and humans are susceptible. So maybe we'll talk about global warming a little bit later. Okay. When we discussed gases, at least we're going to start with the physics of gases. In order to describe the physical behavior of a gas, you need 4 measurable quantities. Right? The first one is pressure, and we denote with a capital P. The other is volume, and then temperature plays in, and then how many particles are there. And that's our old moles symbol. Okay, the number of moles. We had discussed that. Okay. So if you know these conditions, you can completely describe the behavior of the gas, or what state it's in, what it's doing in a physical sense. Or with our equations, if you know 3 of them, you can solve for the 4th one. But actually, historically speaking, the way the gas laws developed, 2 of them would be held constant, and the other 2 would be investigated. You allow one to move. It's like our graphing, where you have an independent variable and a dependent variable. Our first one is going to be pressure and volume. And if we hold the temperature constant and the number of moles constant, and we change the pressure on the gas, then the volume is going to change. And you notice from our graphing experiment, if we increase the pressure, the volume is going to decrease. It's an inverse proportion. Well, first we need to know how to measure pressure. And the simplest definition is pressure is a force per unit area. Okay. Now, if we're in the SI system and using standard, actually it's a derived measurement, the force will be measured in newtons, and the area would be measured in square meters. But pressure is one of those that we had to sort of grandfather in, because Middle Ages, they were working with pressure before we standardized things. So we have a whole host of different units of measure. And we're going to get to that in just a second. The development of these laws tracked the development of technologies for measuring these factors. The first one that came along was in Italy, Evangelista Torricelli. He's obviously Italian. And he invented this device called the barometer. Right? Have you ever seen any kind of barometer measuring pressure? No, you don't have one hanging on your wall at home. No, you do have. Okay. Some cell phones have pressure transducers in them now. Some of the more expensive ones. And they'll give you the air pressure, just read it off your phone. Mine will do that. Well, those are a type of pressure measurement device called aneroid. Aneroid? Or is it an A? I can't remember. What all it means is no liquid. And that's setting it apart from Torricelli's type of pressure measuring device, the barometer, which is based upon mercury, which is a liquid at room temperature. So I think I've got an animation here that simplify things. This was in the middle of the 17th century. There you go. So what Torricelli did was, and mercury came out of the Middle Ages. I mean, the alchemists knew all about mercury, how to purify it, how to extract it from various minerals. Even the ancient Romans were using mercury. They thought it had some kind of magical life-extending properties. They didn't realize when you consume mercury, you're consuming a deadly toxin. Anyway, Torricelli used liquid mercury in his barometer, and he just had a container of mercury, and then he had this tube, glass tube that's shown here, inverted, In these days, glass blowers could produce long tubes and various other things that were uniform diameter. And that's what they did. They produced this long. Torricelli might have been able to do it. I'm not sure. It was a common skill set. And all he had to do was fire one end and close it off. Now he had just a tube with one end open. And he filled it with mercury. Right? He turned it this way first and filled it with mercury. And when it reached the top like that, he put his thumb over it and inverted it and submerged the open end in the mercury, hand and all, and turned it loose. And he saw what happened when he turned loose of it. And let's see, now we're going to have this open end and that closed end in the mercury. And this is open to the atmosphere. And he noticed that when he turned his thumb loose, the mercury dropped. It came down to, well, I don't know, wherever. And it said, and the first thing was, this was the first instance of a vacuum, right? There's matter there, and now there's not matter there. So that's the vacuum. Well, what's holding it up, right? There's nothing pulling on it to hold it up. So he reasoned that there must be something pushing down here that's translated through to hold that column up. And he was right. It was the weight of the atmosphere above, several miles high above, pressing down on that mercury. And this device was used to measure air pressure, right? And at this time, they had access to units of measure in millimeters. So he noticed that on the average, at sea level, it would sustain or hold up about a 100 millimeter column of mercury, a 750 millimeter column of mercury. He also noticed that if we went up a mountain, the column dropped because there was less atmosphere above it. And if he went down below sea level, that it would go above 760. And he noticed up and down depending on his elevation. So that supported his assumption that it was the atmosphere pressure that he was measuring. Now he knew it was pressure. It was an intensive property because it didn't matter how big this thing was, right? Or how big around his tube was. It'd be the same height, whether it was a big vat or a small vat, and a large tube or a small tube, didn't matter. So he was actually measuring an intensive property, pressure. And this is an intensive property, right? Force per unit area. If the area goes up, the force has to go up to meet this constant. Now, once other natural philosophers got hold of this thing, they started doing other experiments with it. And one of the experiments was they just set it on the desk and took measurements over time. And they noticed that when bad weather was on the way, it would start to drop. And when the bad weather passed, it would go back up. Sunshiny day, it'd be up higher. So we still use that today. Low pressure versus high pressure systems. It's based on the good weather, bad weather. There were other ways to use this device also. In fact, some doctors' offices still have those things hanging on the wall, the sphygmomanometers with mercury. They don't use them anymore, but they're decorative. And all you have to do is close this off and run it over here to your patient's arm, right? Pumping up with air, and the pressure that's pulsing in your arteries will relay that pressure to the surface of the mercury, and you'll see this thing bounce. And if you increase the pressure high enough, it'll go up to here, and then as you let off, it'll go here, and then it'll go boom, 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 boom. And if you're listening, you can hear the Korotkov sounds. You come down to, and you hear the last one. You want the first one and the last one to measure your systolic and diastolic pressure. So that's your sphygmomanometer. Well, chemists also use this to measure the pressure of a container of gas. We just call that a manometer. So you can measure the pressure of gas in a container. It could be less than, or it could be greater than that. So now we know how to measure the pressure of gases. Now, the question arises, why did Torricelli use mercury? Well, I haven't read up his complete history, but I wouldn't be surprised if he didn't use other liquids, like water. Water was probably easier to get than mercury. But if you put water in a tube and support it by air pressure, you got to have a tube at least 33 feet tall, right? Because of the difference in densities. Mercury is about 13.5 times as dense as water. So the column is going to be 13.5 times as long, because the air pressure will support a column that high. So mercury was the best choice. Okay, let's see. I mentioned that weather thing already, and I'm wasting too much time. We're going to run out of time, I know. Okay, so we take, this is the value that we take as atmospheric pressure at sea level. And this is one of the units of measure is the atmosphere. 1 atmosphere is equal to 760 millimeters of mercury. So there we have an equivalence. Now we have a conversion factor, right? All you need is an equivalence to make a conversion factor from millimeters mercury to atmospheres or the other direction. All right, these are just examples. The airport down the road is, say, if you measure 640 millimeters of mercury, which is not far off because we're 2,500 feet above sea level, roughly a half a mile. So the air pressure is going to be lower, even on a good day like today. So if I calculate that pressure in atmospheres, what I need is the conversion factor, 1 atmosphere per millimeter of mercury, and I put millimeters of mercury in the denominator, so it'll cancel the numerator and leave us with atmospheres, just like any dimensional analysis problem we've done in the past. And there we have less than 1 atmosphere at, and those are the FAA abbreviations for our local airport, BKW. All right, if we go up to Winter Place, which is about 1,000 feet higher, we should expect the air pressure to be lower, and it is by quite a bit. That's why when you go up and down the mountain, your ears pop. You're changing air pressure. If we go down to, say, Great Salt Lake or Death Valley be better, or to the Dead Sea, then you're going to get a lot higher pressure. Okay. So now that we have, well, there are other units of pressure. Okay, atmospheres, millimeters, mercury. The pressure that I mentioned earlier, newtons per square meter, is actually the Pascal. 1 Pascal is equal to 1 Newton per square meter. The advantage to the SI system, I'm sure I've said this before, is that these units are interconvertible, right? We know what a meter is, right? That's a fundamental unit. We know what a Newton is because it's based upon Newton's second law of motion. F equals ma. Mass times acceleration equals force. So an unbalanced force applied to a mass of a certain amount will produce an acceleration. So if we have a mass of 1 kilogram an acceleration of meters per second squared, then that unit, 1 kilogram per meter per second squared, is 1 Newton. So that would go up here. And they're all interconvertible because we know what their relationship is to one another. But for units of pressure, atmospheres, millimeters of mercury, pascals, and let's see, pounds per square inch. Remember that from grade school? What's the normal atmospheric pressure in pounds per square inch? There you go. That's equal to 1 atmosphere. So we have all these equal to one another. Pascal is a unit of pressure, but it's not 1 atmosphere. So many pascals equals an atmosphere, and I think I got it coming up here. Yeah. Oh, inches of mercury. 29.92 inches of mercury is an atmosphere. And there's, here we go. 100,000 pascals is, so 10, let's see, 1, 2, 3, 4, 5. 10 to the fifth, 10 to the fifth pascals equals 1 atmosphere. Okay. And then the last one is called the bar. And you'll see bars, actually you see the millibars on weather maps. So if your weatherman is talking about or weather girl, weather person is talking about a approaching hurricane or tropical storm, they'll say the pressure at the center of this storm is such and such. And they usually quote it in bars. And the lower it is, the more powerful the hurricane. So let's see. No, I'm sorry. 1 bar. Where did I put it? Here. No, here. This is 1 bar. Yeah, that's 1 bar. And 1,013 millibars. That's 1,013 millibars equals 1 atmosphere. There we go. So that's not true. This is true, but this is atmospheres, atmospheres, atmospheres. We're going to stick with atmospheres or millimeters of mercury. We might use this one depending on how we measure our air pressure in the lab. If I use the barometer on the wall, it quotes it in inches of mercury. So then you'd have to convert to atmospheres to complete the experiment. We'll talk about that later. Okay. So there are a whole host of different ways of expressing gas pressures. And that's just an example of converting from PSI to inches of mercury and millimeters to millibars. Okay. All right. So we need to get to the gas laws here pretty soon. This is something you don't have to do, and I think we don't have time to go through it. This just converts 760 millimeters of mercury to pascals by physically measuring the device, right? So we get all these measurements, density of mercury. Actually, it's a little more than 13.5, 13.59. And water is 1 gram per cubic centimeter. All right. All right, so let's get to the gas laws now. The first one is pressure volume. You've been exposed to that already. That's Boyle's law. That's the one we're going to do next week. We're actually going to measure the volume of a trapped gas with at different pressures. Okay. Boyle's law measures the relationship pressure and volume. And what Boyle discovered in his experiments, in fact, Boyle didn't actually use a barometer. He used sort of a modified barometer. Actually, it would be a manometer. He used a J tube, and these glass tubes were still, everybody in Europe knew how to make them. So he used a J tube that went like this, that, and it was open to the atmosphere. And he just started adding mercury here. And of course, when you add a little bit of mercury, it's going to pool up on the bottom. You add a little bit more, a little bit more. And when it reaches the inside of this curve, this gas is now trapped. That means all that gas in there is all there is going to be in there. So that's constant. The amount of molecules in that space are fixed. And the experiment didn't take but just a few minutes. So the temperature is not going to change. If you want to hold it constant, just create an ice bath and dunk it in the ice bath, and it'll stay constant. As long as there's water and ice together, it'll be 0 degrees C. So that allows him to let these vary and these guys stay constant. So he just kept adding mercury, and he noticed that as he added more mercury, this one didn't get quite as high. So instead of being equal, there's the height of this mercury, of course, the difference in that, plus 1 atmosphere, or whatever millimeters of mercury with the atmosphere. So we could say had a barometer sitting over here and measured the amount of pressure that's being exerted by the atmosphere, and then the amount of pressure that's being exerted by that difference in mercury height, and correlated that to the volume. And since these tubes are uniform in diameter, he could equate height of the column to volume. And he just measured those pressure and volume and got these values here. As pressure went up, the volume went down, and he multiplied them. And he got the same value for each one within experimental error. So to express that in an equation, he just said, okay, it's constant. Pressure times volume is a constant. That's Boyle's law in its simplest form. Okay, so whenever you see an equation where the product of 2 variables is equal to a constant, it's always an inverse relationship. Because in order for that to be constant, if that one goes up, that one's got to go down. You have no other choice. Mathematically, that's it. Okay, so this was in 1662. Let's see. Not too long after, when was Torricelli? Pretty close to that, wasn't it? 43. So it's like 20 years later is when Boyle. Now that doesn't mean Boyle did these experiments at that time, but that's when he published his work. So here's an example. If we have pressure in atmospheres and volume in liters, then we notice that as the pressure goes up, volume goes down. Or in this case, as the pressure goes down, the volume goes up. Okay, so another thing about this is if you graph this, right, pressure here, right, it's the independent variable, volume, and you have these points, and you draw a best fit curve, what you'll notice mathematically is this is a hyperbola. Remember that from math class? Hyperbolas have these tails out here, and they never touch the axis, ever. And that makes sense. When would it touch the axis on the x-axis? When volume was 0, right? If you make volume 0, then it can't be equal to the constant, because the constant's not 0. Right? Now in math, your hyperbolas, usually a hyperbola formula will give you like a double. It depends on the equation. but we're only interested in this part of the hyperbola. And remember how we made it, well, scientists don't like curves if they can avoid them. So if we can transform the data to make a straight line, that's what we did in our graphic sample, right? Remember how we did that? We just took the inverse of that number, right? So I'll show you again. I think I did before, but I'll show you again. If this is a constant, pressure times volume, if we say, all right, what if I divide both sides by a volume, right, that variable? I can do that, can I? Mathematically speaking. So that cancels this volume, doesn't it? And it leaves us with this one. But I don't like the way that's arranged. So I'm going to say K times 1 over V. That's a constant. This is a variable, that's a variable. So now if we change our axis to be pressure versus 1 over volume, we get a straight line. And the slope of that line is our K value. Okay. Y equals mx, and B is 0. It goes straight through the origin. It's supposed to. Okay, that's one of the types of transformations that we can do to make data easier to manage. All right. So I mentioned when we solve these problems, there are two types of problems. There's before and after, and there's a state. We can use Boyle's law in a before and after arrangement to solve problems. In other words, if we have a gas in which we've measured pressure and volume, right? That's equal to a constant at one place. Now, if all the other conditions are the same, if we do this experiment in the same device, right? So we don't introduce other variables. And then we change the pressure to another, right? A different pressure, it's going to give us a different volume, right? Okay. But it's still equal to K, isn't it? Right? Because as we increase the pressure, the volume goes down. We increase the pressure here, volume went down, it's still equal to K. Both of them are equal to K. So it's that math, what's that math law? If A equals B and B equals C, then A equals C. Is it cumulative property? No. Proportional property? I can't remember what it's called. You get the idea. So what we've got here is a solvable equation. If we know the conditions before, right, of this pressure and this volume for the gas, and we change the pressure to this one, we can solve for that one. That's a before and after. It's like any algebraic expression. If you've got one unknown, you can solve for it. Okay. So that's what the PI is. P is initial and F is final. And here's an example that I don't have time to talk about right now. We just arrange the equation. What you do is when you got your word problem, you say, all right, what am I given? Do I have, I do it like this, final. And I say, what are my values? What's the initial pressure? Calculate the final volume of gas when 15 liters of gas at 500 millimeters. 15 liters at 500, better than that. At 500 millimeters of mercury is changed to a pressure of 125 millimeters of mercury. So final pressure is 125. That's our unknown. Okay. So if this is our unknown, then we just solve for that one and plug in the other values. And that's what we've done there. So when we plug in the values, we get 60 liters. Now, is that reasonable? If the pressure went down, the volume should go up. Pressure went down by this much, volume went up. Okay. That's a before and after Boyle's law. Here's another one. Now, notice that the units of measure only matter insofar as they have to be the same on both sides. So any measurement we use for pressure has to be the same. Any volume pressure has to be the same. Any volume measurement, excuse me. So it doesn't matter. We can use any measurement of pressure, any measurement of volume, and we'll just get, say, in this case, we have liters for volume, so our answer is going to be in liters. Okay. In this case, we have cubic feet and pounds per square inch. Doesn't matter, still works. Just plug in the values, you find which one you're missing. In this case, the final pressure is missing, so we solve for final pressure. Plug in the values, and the final pressure is that. Okay. You got lots of those to work in that review document, give you practice. Okay, that's Boyle's law, pressure volume. Now, and Boyle came first with his law, largely because of the technology. We're able to measure the pressure of a trapped gas and able to measure the volume easily. So that it just made sense. That was the first law. When Charles came along, he was a Frenchman. When Charles came along, somebody had to invent a reliable thermometer. Right? So for chemists, the reliable thermometer would be in Celsius. In fact, in honor of the inventor, Celsius, and his scale. 0 degrees is freezing point of water, 100 degrees is boiling point of water. And you have 100 divisions in between. So once we had a way to measure temperature, then Charles could, in 18th century, I think it was. Yeah. Well, he and another Gay-Lussac also worked with it too. In fact, Charles did the work and Gay-Lussac published the work along with some other things he was doing, and he gave Charles credit for it, even though there was no publication. So that's why it's called Charles' law, even though Charles didn't publish it. I'm entitled to do it that way. At least that's the way I learned in English. Now they add apostrophe S on everything. Right? I guess they're trying to standardize the methods. Anyway, now that we had a reliable way to measure temperature and we can still measure volume, Charles investigated the relationship of volume and temperature, and we had to hold pressure and moles constant. So now we're doing volume and temperature. So how would you, temperature is easy to control, like water bath, or just do it really quick or go down in a cave, right? Where the temperature stays the same all year round. But how do you hold pressure constant? That's a key. One way is with a cylinder of a uniform diameter and put a plunger in it, or a cylinder with a piston in it. And then just put a mass on it, like a kilogram. Right? That plus the atmospheric pressure is constant. And then, of course, the number of moles is constant because there's no way for the air to get in and out. And then you do something to change the temperature. And once it's equilibrated, the temperature here is the same as the temperature in there. So now we have a way to measure volume against temperature. You just measure where that cylinder moves, the piston moves, and the temperature that you've applied. So you can track your data, like your data points. Change the temperature, measure the volume. Temperature is your independent variable. And what Charles discovered was that temperature against volume gave him a straight line. Let's see. Here it comes. Okay. Notice that the straight line doesn't pass through the origin. That's because we're using a temperature scale of degrees Celsius. So the temperature can go negative. Out here is positive values, over here, negative values. So if we kept going, we could like use, say, ice water with salt in it, like making ice cream. The temperature is going to drop into the low teens. All right, so you can still measure, you can keep measuring it down into the negatives. Okay, that's okay for measuring temperature versus volume. But if you're going to say the Charles law is actually volume divided by temperature equals a constant. In other words, as the temperature goes up, volume goes up. As the temperature goes down, volume goes down. The problem, though, is if you measure that temperature in negative values, that blows your constant, because now your constant suddenly turned negative. So we can't use degree C. What we have to do is find a system that will give us temperature with all positive numbers forever. Right? And that's the Kelvin system. Lord Kelvin was working with thermodynamics. It was an emerging science in the late 18th century. And he proposed a system with all positive numbers. And his zero value was not the freezing point of water. His zero value was absolute zero. So if you keep following this out here, remember, this is anything in here is interpolation. Remember that? Anything out here was extrapolation. So he extrapolated this down to where volume was zero. Theoretically, gases never reach zero volume because they have molecules in it. But theoretically, this point out here would be minus 273 degrees C. That's his new zero point. So now if we work with Kelvin and say this is zero, the zero on the Celsius scale is going to be 273 Kelvin. Okay. Now that you've got all positive values, this works. That law works. Okay. All right. That's why whenever we do our calculations, they have to be done in Kelvin, not degrees Celsius. Now you can measure in Celsius, of course. There are no thermometers I know of that'll measure Kelvin because you can't find the zero point. How are you going to get to absolute zero with the gas or with anything? Absolute zero is theoretically the point at which there is absolutely no kinetic energy. Right? So how do we make things colder? Just think of your air conditioner at home or in the car. You take the heat from inside the vehicle or inside your house and dump it outside. Right? So it has to be dumped in such a way that the dumping mechanism is at a higher temperature than the outside. Right? So that's where we send a freon through the house, send it through an evaporator coil and cool the house. Right? It changes from a liquid to a gas. And then we go outside and pump it and compress it again, make it hot, and then dump that heat into the outside. So you can get down pretty close, right, to absolute zero, but you never get there because there's nothing colder than absolute zero. There's no place to dump the heat. Okay. So it's theoretical and there's no thermometer that'll do it. But what we have to do is convert. So once you've got your temperatures in degrees C, convert them to K equals to degrees C plus 273. Right. We did this earlier, didn't we? Yeah, I thought we were talking about thermometers. Okay. Right, and there's what it would look like in animation. Now, of course, Kelvin went, I've got his paper, his original paper, a photocopy, of course. And it discusses how he came up with this system And this is a very simplified discussion. I mean, he went into mathematical detail so that he could publish it and prove it to his colleagues, and so it would be adopted. I mean, this is not a good enough explanation to get the whole scientific world to believe what you're telling them, right? But it's good enough for classroom discussion. All right. So Charles then came up with Charles' law. And if we do the same things we did before, say this is equal to 1, 1 equal to. There you have your before and after equation. V1 over T1 equals V2 over T2. And if you know this one, and that one, you can solve for that one, for instance. Okay. All right, here are various examples. All right, I'm not going to stop there. In fact, if you go back and look at some earlier videos, you'll probably see I did. When I had time, I slowed down and talked about them in more detail. But right now, we don't have the time. I'm going to run over anyway. Okay. The temperature always has to be in Kelvin. Now, if you run across a problem that requires that you start in Celsius and end in Celsius, you got to convert to Kelvin, do the calculations, and then take the answer and convert back to Celsius, which would be Kelvin minus 273 is Celsius. The nice thing about that is, well, I've said this before, the size of the Kelvin degree is exactly the same as the size of the Celsius degree. The only difference is the 0 point. All right. So let's see, where are we headed here? Avogadro's law. Okay. Let's see, let's clean this up. We're going to hold 2 different ones constant and let 2 of them vary. Avogadro was an Italian. I think. Have I described Avogadro's law to you yet? I can't remember if I have or not. I guess it bears repeating. Anyway. Avogadro's law was one of those also that was his postulate, but it was disseminated by a student, Cannizzaro. And Gay-Lussac used it also in his research. So Avogadro proposed that if we hold pressure and temperature constant, and let volume vary with the number of moles of gas. So if you put twice as many moles in the container, you're going to get twice the volume. So what we're saying is they're directly proportional, equals a constant. And you can do the before and after thing. And there, all you have to do is hold the temperature constant, so we don't have to worry about converting temperatures to Kelvin with Avogadro's law. The other way it's often expressed is, I feel like it's deja vu. I've done this before. If you have 2 volumes, have I done this? Yeah. If you have this volume equals to this volume, and the pressure inside is equal to the pressure inside of this one, and the temperature is the same in both of them, then the number of moles in each one must be the same. That's another interpretation of Avogadro's law. And it led to an explosion in chemical innovation in Europe after 1860. Okay. So here's where we can make a connection with stoichiometry. Because remember, stoichiometry is based upon number of moles of reactants and products. And if they're all gases, now we have a handle. Like this, for instance, this the Haber-Bosch process. Actually, this one's in reverse. These are all gases plus H2. And we have 3 of these and 1 of those. This tells you the molar relationship. If you start off with 2 moles of ammonia in your container and you decompose it, so it's all gone. So you start off with 2 moles and you end up with 1 plus 3 is 4 moles of gas, right? So you got twice as many moles in the product as you had in the reactants. So what should the volume be? It should be twice what it was before. Okay, so that's our lead into stoichiometry. In this case, we're starting off with 35 cubic feet. We should end up with 70 cubic feet. Okay. We double the number of moles, we should double the volume also. All right. Now for the combined gas law. This is still a before and after situation, but we're going to combine all of these laws together. So it broadens the application. We'll start with Boyle's law. Like P1 V1 equals P2 V2. We also know that Charles, the relationship is volume to temperature. Okay. And Avogadro is this one. So now we have a combined gas law, all these variables. And in order to solve it, of course, you need to know everything except for one. We don't solve 2 unknowns in this class because you need 2 equations, remember? So if we know the before conditions here and we know 3 of these, we can solve for the other one. That's the combined gas law. So here we begin with Boyle's, and the animations take us through adding Charles and then adding Avogadro. Now that we have this situation, we can move into a state situation, a state function with the ideal gas law. Notice that these are both equal to a constant. Okay? So they're equal to a constant. And if we know what that constant is, then we don't have to know the before or the after. We just need to know what's right now. This is right now, and that constant. So how do we determine that constant? Well, we have to be sticklers about the units of measure. And we measure, say, pressure is 1 atmosphere. I'll give you the volume in a minute. 1 mole, right? And standard temperature for gases is 0 degrees Celsius. Standard temperature for everything else is 25, but for gases it's 0. So that's 273 K or 273.17. So when you have these conditions, what's the volume of your gas? And remember, all these gases act alike under these conditions. Right? It's 22.4 liters. So if you multiply those out, you get this number. And the units of measure are liter atmospheres per mole K. Okay, so there's our constant. We know the constant here. If we can figure out 3 of those, we can solve for the 4th one, and it doesn't matter how it got there. Right? We usually give this a special letter, R, and you'll often see the equation. Let's see. Did I give it to you here? All right, we'll talk about that in a second. You usually see the equation like this in linear format. There's your constant. There's the moles. There's the temperature, because they were in the bottom here. Move them over there. PV equals nRT is the ideal gas equation. Now, what is an ideal gas? All right. It has to remain a gas under all conditions of temperature and pressure. We know that's not true, but that's the ideal. It has a point molecular volume. What does that mean? Remember geometry? When it talked about, at least I remember this. That's a point. It has no dimensions. If we draw a line, it has one dimension. Right? If we draw an object like that, it has two dimensions. And if we draw an object like this, it has three dimensions. The point has no dimensions. That's another way of saying that the gas has no volume. Point molecular volume means zero. It does not interact with other gases. In other words, when they do impact, and they do, we take that into account. When they do impact one another, they just act like billiard balls. They just bounce off. They don't have no interactions, attractive or repulsive. And of course, they have to obey all the gas laws. A real gas, when you put it under pressure and cool it, it'll eventually turn into a liquid. And some of them turn into a solid. Right? You've heard of dry ice? That's solid carbon dioxide. So when you take a chunk of it and set it on the desktop, it goes from solid straight into gas. That's called sublimation. They do have an actual volume. They do interact with one another, sometimes very strongly. And they also interact with the walls of their container. If they didn't do that, we couldn't measure the pressure, because that's where our pressure gauge is located. That's a real gas. Now, there are conditions under which we can treat a gas as an ideal gas. And that is under conditions of low pressure, high temperature. And as a sort of a corollary to low pressure is low moles. You don't have to try to stuff a whole lot of gas into a small container. Under those conditions, real gas behaves like an ideal gas. Okay? Low pressure means that there are fewer impact events, so the gases don't interact. High temperature means if they do interact, they're moving so fast they don't care, right? They just smack and go. And then low moles also means that the interaction is very infrequent. Now, under what conditions do you find these? Low pressure and high temperature. Here, right here. Relative to Kelvin, we're at 298. If we're 25 degrees, we're 298 Kelvin. That's high temperature. Pressure. 1 atmosphere is low pressure relative to 10 atmospheres, 100 atmospheres. So it's relatively low pressure. And that's why all these gas laws worked in the 17th and 18th centuries. But the scientists really didn't know why. They just knew that gases behaved alike. We came up with this one later. Okay. So we combine all these into the ideal gas equation. Actually, it was first proposed by Emil Clapeyron. You probably see that name again, maybe not this semester, but the next semester. So there's your ideal gas equation. And if we use liter atmospheres per mole K, we have that 08206 is our constant. But if you use different units of measure, you're going to have a different value. And for some of the work that we're going to do, we're going to use 8.3145, which incorporates an energy value, joules, rather than liter atmosphere. So I'll let you know when we're going to use it. You don't have to freak out about it right now. Okay. So what that also means is when you solve this equation, this has to be pressure in atmospheres. This has to be in liters. That's got to be in moles, and that has to be in K. And these units are dictated by the constant. Right? That's one of the stipulations. If you're going to use a state function like this, then you have to pay attention to the units of measure. Whereas with the others, except for temperature and Kelvin, the others, it didn't matter. You could use anything because we knew before and after. But if you're at a state function, we're relying on the units of measure for that constant. These have to correlate with it. They have to be cancelable. All right. So there are various rearrangements that you can make. Sometimes you may want to know a ratio instead. Right? Say you want to know moles to volume. So you can set it up like that. Okay. Or find out what an R is. If you use different units of measure for pressure, volume, moles, and temperature, then it'll give you a different R value. All right, these are examples. We don't have time to stop here, I'm sorry. Okay, so this is a stoichiometry problem. I'm out of time already. 4 minutes. If you have to go, that's fine. I'll keep recording. So if we have this mercury 2 oxide and we heat it, actually you can put it in a bell jar in a container and heat it with a magnifying glass. That's the way they used to do it. And mercury 2 oxide will decompose into mercury liquid and oxygen. And you know when it's gone because mercury 2 oxide is red. And of course, mercury is kind of silvery metal, oxygen is a gas. So you can produce mercury and oxygen from this experiment. So if we calculate the mass of the HGO needed to produce 220 cubic centimeters at 25 degrees and 740 millimeters of mercury, we know we have to convert cubic centimeters into liters, right? Milliliters into liters, just move the decimal to the left 3 places. And 25 degrees C into Kelvin, just add 273. And then millimeters of mercury into atmospheres, use that conversion, divide by 760. Then we can put it in our equation, and that calculates the moles of oxygen. How do we know that we can do that? Because the only product that's a gas is oxygen. So if we use these values and determine the moles of oxygen, now we can back figure to the mass of, well, the moles of HGO, and then convert it to mass, right? It's a stoichiometry problem. You can't move anywhere in that equation unless you're moles. So we take oxygen and find the moles of oxygen produced. Right? That's the way you solve it. Okay. And we find that there, let's see, come on. Here we go. There's our conversion. And we find that many cubic centimeters of mercury. I thought we were looking for mass. Oh, what volume of mercury? Okay. Yeah. Once we find out the mass of mercury, then we have to convert using its density. Remember the equation? Density equals mass divided by volume. We know the density, now we know the mass, we can find the volume. That's okay. You're not hurting my feelings. Okay. So those are the gas laws all the way up to the ideal gas equation. And now we can use these gas laws to determine molar mass by the Dumas method. And this is not Dumas of the Three Musketeers. This is a different Dumas. This one's actually a scientist. Jean-Baptiste André. They like a lot of names, don't they? He was renowned for accurate determination of molar masses by this method. He and his laboratory. He did a bunch of other stuff too, or organic chemistry, but he determined molar masses for lots of compounds. Yeah, good. Okay.
Have a good weekend.
You too. Let's see, that's a lot of history. So if we, and this is when we get to do the Dumas method, which I think is coming along, our last lab is the Dumas method. We're going to incorporate the ideal gas equation, conflated with molar mass, which is used to be called molecular weight, is mass per moles. So the variable that they have in common is this one right here. Right? So if we solve this for PV over RT and substitute this one right here, then we get mass divided by PV over RT. And then remember, the denominator of the denominator is the numerator. So this one, it flips and we get mass times R times T over PV. And that's the molecular weight or the molar mass. So if we know the mass of the gas that's in the container, we know its temperature, we measured the pressure inside, which in our experiment would simply be atmospheric pressure, and we measure the volume in the container, then we can calculate the molar mass for a volatile liquid. Okay, there it is animated. All right. So here's an example, and I think I'm going to save this until we actually do the experiment because we'll talk about it more then. But these values were obtained during an experiment, and this converts all that information. And we find that the molar mass of this compound is 152.98 grams per mole. This is one of the ways, and we were doing empirical formulas to molecular formulas. We needed to know the molar mass of the compound by some independent method. This is one of the ways you do it. If the liquid is volatile, then you can fill it up in the gas space and measure these values and determine its molar mass. All right. Let's see, ideal gas law under changing conditions. Okay. This is okay. This is a discussion of goes back to before and after, and it tries to draw. I need to change the slide. It tries to draw the equivalence of initial versus final. So we're going backwards. This is before and after. We've already talked about this. All right, so there you have, and all you need to do is with that combined gas law is know all those others, and you can solve for the missing one. And that's what we've done here. In this case, we find that the number of moles before and after are the same, so they go out. Right? They disappear. And now that means we can solve the equation. Okay. This is using the ideal gas equation in a chemical reaction. And actually, we've already done one of these. Yeah. Well, we did one with the ideal gas equation. You can also do it before and after. Okay. Now let's do Dalton's law of partial pressure. This is going to become very useful. This is the same John Dalton that proposed the atomic theory. So he wasn't just working on that all the time. He was working with the gases too. And what he proposed was that the measured pressure of a confined gas mixture is actually the summation, the mathematical addition of all of the individual pressures of the gases that are contained in the vessel, up to however many. So if we have an atmosphere, if we have 1 atmosphere gas, that say we're at sea level and we've got 1 atmosphere pressure, and we know the percent composition of the air that we breathe is 21% oxygen and 79% nitrogen, and 1% about argon. Then we know 1% of 1 atmosphere is 0.01 atmospheres, right? Argon. Let's see. Yep. 21% would be 0.21 atmospheres of oxygen and 0.79 atmospheres of nitrogen. Okay. Based on Dalton's law, add those up, and that discounts the minor components like carbon dioxide and methane. You know, if you got a lot of cows farting. So what this equation tries to do is equate. We solve the ideal gas equation, PV equals nRT. nRT. We solve it for pressure. That's nRT over V. And then we apply that to each one of these pressures. And each one of these pressures is the number of moles of gas of each one, which will be different, right? This changes. R doesn't change, temperature doesn't change, total volume doesn't change. So the pressure is due to the number of moles of each gas. So that's what we're trying to show here. The total number of moles is ratioed by their pressures. So if we know this ratio, then the total number of moles here equals the moles of 1 plus the moles of 2 plus the moles of 3, and they're all related by their pressures. So, well, we've already said percent here. Let me go ahead with continue with this one. So the other way to express the amount of gas in a mixture is this term called the mole fraction. So the mole fraction of 1 is simply the number of moles of 1 divided by the moles of the total. That's the mole fraction. And if you have the mole fractions of all the gases, add them up, they should equal 1. Okay. And the mole fraction times this total gives you the pressure. Because if N divided by N total is that, it's also equal to the pressure of 1 divided by the pressure of total. So mole fraction times total pressure equals the pressure of that gas. All right. So if for a practical example, we've got C3H5N309, which is nitroglycerin. And you watch enough movies like I have, you know that nitroglycerin is not something to be messed with. I remember there was one John Wayne movie called The War Wagon. You ever seen that one? They were going to blow up a bridge so that they could take this wagon full of gold going from the mines to the railhead. And they were going to make him go through a different route. So they had to blow up a bridge. So he couldn't cross the canyon. He had to go way, way around. So one of the guys in John Wayne's team knew how to handle nitroglycerin. At that time, dynamite wasn't real common. And besides, the fusing dynamite was a little precarious. But if you put nitroglycerin in a pint whiskey bottle and you set it in the bridge and you got a tripwire, then when the horse kicks the wire and yanks that bottle and it slaps against the bridge, it'll blow up instantly. So that's how unstable the stuff is. You have to keep it cold and undisturbed. Okay, so here's the reaction of the decomposition of nitroglycerin, right? 4 moles of nitroglycerin yields 12 moles of carbon dioxide, 10 moles of water, 6 of nitrogen, and 1 of oxygen. So you went from 4 up to 27, from 4 to 27. 4 moles of nitroglycerin, 27 moles of gas. So that's a huge expansion. There's energy released also, but the main explosive effect is the fact that you're producing that much gas very quickly. So let's we don't want to blow the lab up, so we're going to take just a small amount in a 100-liter vessel and at 25 degrees and 20 millimeters of mercury. So we've sucked a lot of the air out of it, and we put this nitroglycerin in it, and then we detonate it inside that cylinder. And the cylinder expands a little bit. It expands by 10% to 110 liters. And now the temperature is 400 degrees. So it is an exothermic reaction. It produces heat. So we want to know what's the pressure, the final pressure when we get finished. All right. So here we've got our combined gas law. We know the before and much of the after. And the ratio of the final moles to the initial moles, the NF and the NI, is 27 to 4. So we put those into the equation also. Okay. And we find out that we went from 20 millimeters of mercury up to almost 300 millimeters of mercury. All right, so half an atmosphere inside that vessel. All right, so what am I doing here? Oh, partial pressures. So if we want to find out the partial pressure of the final, then all we have to do is say, all right, we have 29 moles of gas at the end, and carbon dioxide contribute 12 of those. So 12 to 29 is the mole fraction. So that means carbon dioxide contributes 123 millimeters of mercury. Water contributes 100. Nitrogen contributes 61, and oxygen only 10 to the final pressure. And if we add them all up, we should get the total that we started with. Close. All right. So after all these laws came into being, a theory was proposed to explain why the laws work. And that's the kinetic molecular theory of gases. Now, we don't have time to go into the history of that, but we draw all those laws together and we say, all right, here's what they have in common and here's why they work. These are the basic postulates. Large numbers of particles, called atoms or molecules, in the gases. Right, we covered that already. The particle size is small compared to the distance. The gas particles are rapidly moving, and they inevitably collide with one another, but they do so as if they were billiard balls, no interactions. And they collide with the walls of the container. That gives us the ability to measure pressure. And we're saying that temperature is the measure of average kinetic energy for all the gases, everything in the container. Temperature is proportional to the average kinetic energy. Now, if you've got the same atoms or molecules, I mean, it's not a mixture, it's pure substance, then you're saying that they all have essentially the same velocity. We know that's not true, but the average is true. And then, of course, if you have a light gas in there, like hydrogen, mixed with a heavier gas like methane, then if they have the same kinetic energy, this one's going to be moving faster than that one because this one's heavier. And I already said this one, they don't interact. Those are the postulates of the kinetic molecular theory. Then we can get into actually calculating, since we're assuming that these atoms and molecules have kinetic energy, we can calculate their kinetic energy of individuals and then average them together, say on a theoretical basis. We're going to use billiard balls. Got to go? Okay. Yeah, I'll finish it up. We're going to start off with 7 balls, and each weighs 5 kilograms. So what is that? 2, 10, maybe 12-pound bowling ball. That's about right. And if we use the kinetic energy formula, we can calculate the energy for each one of these balls at different velocities. Okay. So here are the list of energies for each one. And the average of the velocities would be about 40 meters per second. Right. But remember, temperature is not a measure of average velocity. It's a measure of average kinetic energy. I'll just pretend there's somebody here and keep talking. So if we calculate the average kinetic energy, we'll add all these up and divide by 7, then we get 5,000 joules is the average kinetic energy. That's the value that's related to temperature. Now, if we say we want to calculate the velocity from our equation, and joules equals kilogram meter squared per second squared, then we extract out velocity, then we get this formula of the square root of 2 times the kinetic energy divided by mass equals velocity, and we plug in the values, and we get a calculated velocity if we use 5,000 joules as our energy. Here, we ended up with 44.72 meters per second is the average velocity to give us the correct average kinetic energy. So there's a discrepancy here. If we just average the velocities, we get 40. If we base it upon their energies, we get 44.72. So we have to modify our thinking and our formulas in order to give us the correct energy by measuring velocities. And this is where the concept called root mean square comes in. Now, this goes into a little more detail. If we want to actually calculate the energy of any particle, we have to know what it's doing in 3 dimensions. You know, what's its velocity that way? What's its velocity this way? What's its velocity that way? If we could do that, then we could calculate its energy. But a simpler way on an average scale is to use the concept called root mean square. So how do you do that? Well, you take a list of numbers, right? Take a list of numbers, whatever values here, and you square them, right? So you get another list of values. You square those. Then you take the average of those squared values, right? And then you take this value and you just take the square root of it. So that's the root mean square, do it backwards. You square it, take the mean of it, and then take the square root of it. That gives you 44.72 rather than 40. Okay, now here's the relationship of root mean square velocity, which is that mu. This is the symbol that's used for velocity. How fast is it moving? Root mean square velocity is actually equal to, for gas, root mean square velocity is, let's see. They did it like this. I want to be consistent. Is 3 times the ideal gas constant times temperature divided by the molar mass. Now, in this case, R is going to be 8.3145 joules per mole K. All right. And since we're in standard SI units, this calculation, if this is K, and this is 8.3145 joule per mole K there, then molecular weight is going to come out in not grams per mole, but kilograms per mole, right? Because these are all standard measures. So to express it in grams per mole, you have to divide by 1,000. Okay, so let's find out what's the average velocity for air molecules at 37 degrees. What we need is an average molecular weight of air. And there it is. We just calculated it. And it has to be in kilograms per mole, remember, in order to fit in that equation. So when we do that, and we substitute it in our equation, right? There's our 3, there's our R, right? There's our temperature, and there's our kilograms per mole in the denominator. And we calculate that the root mean square velocity, our average velocity of our molecules is 516.33. So that correlates to 37 degrees. If we increase the temperature to say 40 degrees, that velocity will increase. And if we cool it, that velocity will decrease. Remember, that's an average. That's a calculated average. All right. Put it in miles per hour, 1,155. So what's the speed of sound at sea level? It's like, what, 720 miles an hour? Something like that, 760 maybe. Or maybe it's even less than that. But it's definitely supersonic. And of course, if we put lighter molecules in there than air, they're going to be moving faster because they're at the same temperature. They have the same kinetic energy. That means they have to be moving faster. Let's see, was that miles? Oh, meters per second. I'm sorry. Let's see, about 1,000 meters per second is closer to 1,100 meters per second. So the first one is subsonic and the second one is supersonic. All right. Now we've got one more law. Graham's law of diffusion. Sometimes it's called Graham's law of diffusion. There's a difference between diffusion and effusion. Diffusion is simply the way a gas moves through another body of gas. Effusion is the movement of a gas through a barrier of some kind. Okay, so if these two gases, A and B, are at the same temperature, and we use the equation, velocity times time gives us distance. Remember? Distance traveled over a period of time equals velocity. So the distance traveled is velocity times time. Okay? So that's where those two equations, and we ratio the velocity of A to B, which also gives us distance of A to B. And the velocity is equal to 3RT over molecular weight. We're going to rearrange this equation because there are cancelable values in there. So what we get is the square root of the molar mass of B divided by A is proportional to velocity of A, B, or distance of AB. So the experiment is we put two gases in a tube, and we have a long glass tube. And we put two gases in that tube, say hydrogen chloride in this end, gas, and ammonia in this end, gas. And where they meet, they will form this solid, ammonium chloride. So we can see them kind of like a fog. And we can tell where they meet. Right? We use a cotton swab and soak it with these gases so they start to diffuse toward one another. And where they meet gives us the ratio of distances. So the ratio of the distance of ammonia to the distance of hydrogen chloride is the molar mass of hydrogen chloride divided by ammonia. Take the square root of that. So there we have our molar masses. Hydrogen chloride is heavier, so it's not going to move as fast. So we should say maybe right in here somewhere is where they're going to meet, because ammonia is going to move faster. 1.463 is the ratio. That's the ratio of this distance to that distance. Right? So this distance of ammonia and this distance of HCl is calculated to be 1.46. Okay. So if we have a 150 centimeter long device, then we know that this one is going to travel 1.46 times as far as this one is. And we can calculate how far the hydrogen chloride moves and how far the ammonia moves. So there you go. I moved it a little too far. It's probably right in here somewhere. Okay. So we can use this to find out what our unknown is. We use the calculations taking our gas as the unknown. So the molar mass is going to be unknown. And we're given the ratio of distances. Right? And there we have our unknown. The molecular weight of the unknown gas is that. We calculate what it is at 128 grams per mole. And then we look at our choices and we find out hydrogen iodide would be our best choice. Okay. This Graham's law of effusion was used during World War II and afterwards with research. to separate the isotopes of uranium. Remember, we were trying to, during the Manhattan Project was devised by the federal government to produce enough fissionable material, uranium material, to make an atom bomb. And since the percentage of U-235 in the whole is less than 1%, we needed an effective way to concentrate the U-235. Now, chemically, it would be near impossible because uranium has the same, U-235 has the same electronic structure as U-238, and their chemical differences are not great enough to economically separate them. So one of the ways to do that was using Graham's law. And what you needed was a barrier with very fine holes in it, very small holes. And you have a mixture of U-235 and 238 on this side with 0.72% here. Okay, so the smaller, the less massive isotope is going to move through the barrier quicker and become concentrated on this side. Not by much, just by a little bit. So what you would do is you would stack them. Stack the barriers. Thousands of them. And under high pressure, they would be forced through like that. And the this material here was part of it was shunted back over here just to maintain equal pressures. But eventually you get down here to a concentration of 95%. You can make a bomb now. Well, if you need thousands of these things, you need a huge space. And here's the difference in velocities, 1.004. So 0.4% would probably be the concentration factor for each stage. Right? So it takes a lot of them. Now, the method was dependent upon finding a barrier that would not be corroded. Uranium, the temperature would have to be much, much too high to make uranium a gas. So instead, the uranium was converted into uranium hexafluoride, which became a gas at a much lower temperature. But all fluorides are very corrosive to things like stainless steel. So it was up to, fortunately at the time, DuPont scientist named Dr. Plunkett had invented this polymer that was made of Teflon. And all they had to do was fabricate it in such a way that you have these tiny pores in the Teflon. And Teflon would not be corroded by the fluoride gas. Right? So I used to live in Oak Ridge, Tennessee when I was a kid. And for entertainment, these facilities where they were doing this research, this was in the late 50s, early 60s. They were still under very high security. So they had these fences around them and armed guards, and they would shoot first and ask questions later. But there was a service road that went around each one of these plants. There were several of these plants. This particular one, K25, was devoted to this method. And it was huge, 44 acres. And most of it was these filters. So we would drive around this thing, right? My family wasn't real rich, so we'd all hop in the car, all the parents and the kids and we just take a drive around the plant. And it would take us 15 or 20 minutes to do it. It was so big. This was one of the methods that was used to purify or concentrate U-235. Now we can do it much cheaper and more efficiently by using ultracentrifuges. In a different plant, that method was being investigated, and in a third plant, they were investigating cyclotron research. In other words, isolating them by mass spectra. And if you want to find out more about this particular plant, there's your link. Okay. Ideal gases, as we mentioned before, have these characteristics. And real gases have these characteristics. So, when we're not under ideal conditions, low pressure, high temperature, say you're low temperature and high pressure, or just high pressure, then you need correction factors. And this was devised by a scientist named van der Waals. And he proposed this equation well, it was before 1910, and was given the Nobel Prize in 1910 for his work in physics. So here's the equation. You'll notice that here's the P term, right, with this pressure correction term, PV, and here's the volume correction term, PV equals nRT. So you need these factors to correct for non-ideal conditions. And you're not going to have to memorize these. This just illustrates what can be done. If you were engineering students, yeah, you'd eventually have to memorize this thing and learn how to use it. All right, that's it for gases. Next Tuesday, we'll review and have a lab. We'll have the Boyle's Law Lab. So have your notebooks, your lab notebooks prepared and ready to go. I'll check them. And when you do the experiment, you're only going to be working from your lab notebook. Cannot use the hard copy. Lab notebook. Put everything in your lab notebook that you're going to need to do the experiment, because the hard copy is going to stay on your desk or at home. All right. That's it for today.